Okay, yeah, thank you so much. I will talk about a little bit what we have been doing in the DTCC. So these are really practical results where we are right now. I'm talking about the digital twins connected to the design process. It's great to have this kind of keynote before, so we are all in the mood and we heard about where we are and the stuff. So I don't need to talk about that really. How to connect people, processes, and ecosystems. So being a very technical person and worked with this technology for a long time, I start to know that the problem is to scale it up. I mean, we are doing solution over and over again, but how can we involve people and how can we be better at sharing knowledge? So I want to talk more about process and a little bit about systems and ecosystem thinking, how we can connect stuff, because we cannot really have the integrated system that we dreamt about in the last 10 years. We need to kind of have the interface to the integrated system, but then the system is everywhere. Yeah. So I tried to change to the next slide. Yeah, okay. Okay, so I just generated this image from Dolly, and that's one thing. Just I did it, and it took me less than 1 minute, and I put it here. So it's flawed, but the thing is that this kind of generative AI is part of what I'm proposing as a solution. It's not the solution itself. But I can use this image actually to explain a little bit on the thing. It's not perfect, but still. Its interoperability is broken. And what was good with this image is that it has human in the center. So usually we have a database in the center if we are technical persons, but yes, so the humans are there. And the problem is that there's a new human coming in here and it is also going to help, but there's a long way to go to the existing expertise. Because we accumulate a lot of knowledge and how we talk, and we make our process more and more efficient in the group. But then there's a new person coming in. It's like, yeah, you also have to spend 5-10 years like we did in the group to go there. But I think we need a highway for new people to go into the existing knowledge in the state. So we need to shorten this with some kind of process to actually speed up gain knowledge. And here on the other side, we have technology, which is super complicated. So we need to speed it up. So the two corners up there are the solutions for interoperability that we have been working with, and that is semantic technology, how we put meaning into the words and how we communicate and how we understand each other. So on one side, we have the interoperability with the, like, let's say, logical rule-based interoperability. And some people call this ontologies or conceptualization of the world and stuff like that. And this can be done in a technical way so that the system can, let's say, can understand what we are talking about and humans can understand what we're talking about. Now, on the other hand, it says human, but I mean more like an AI assistant, which we will see like exploding now with the large language model. And this is another kind of semantic connection, which is more mathematical with vector-based calculation. So if you know about embeddings and large language models and transformers, this is another way. So these two kind of semantic technologies, I think, is what we are using in this solution. So a workflow to build semantic interoperability as a continuous process. This is what we have been talking about in our group, basically starting from zero to have a collaboration in the AEC to talk about things like building, space, a room. What is that? What do you mean? Do we put it in the tool? And if we transfer it to another tool, did it still mean the same thing or is it misunderstood? So the tool I will go through now, and this is going to be a movie. And this is a tool that we have built from Paramountic called Base Bucket. So before I start the video, I will try to speak over it. You can see how things are moving. This concept is called Base Bucket because you have bases and you have buckets, and bases are things like buildings and whatever, like the twins or systems or whatever things. And buckets are the insights and the extracts from the data. So we are connecting this stuff with nodes on the interface, and then we break everything down and we go into the different parts of the workflow using this interface. And in this case, we're going to connect something called Speckle. So if you don't know, I was hoping that someone else would present before me and explain what Speckle is, so I don't have to explain. But yeah, let's go, and then yeah, Speckle is a open source collaboration platform to connect Revit and Grasshopper Rhino and Excel and Power BI and many different tools. So it's really cool because it's open source and has a great community around it. So in the user interface, we start to create a base, which is basically the Speckle server itself. So that's a thing, and we connect it. I just changed the name to Speckle server. It's the name of the server created by White, and then what we can see here when we have connected to the server. Now also want to go into the server on Speckle. Here is the Speckle interface. So I go over to that system and I see in Speckle you have projects, you have models, you have versions, and you check in from Grasshopper, from Rhino, different models. And on the canvas here, we go back, we see that it's mirrored here. So we have everything in the Speckle server, you have it here as well. And if you know about Speckle, you know that they call the terminology is streams, branches, and the commits, which is from Git. And now they changed it. So now they call it projects, models, and versions. It's much better talking about concept. So we are using the terminology that we like. So now I'm going in here and I'm going to drag out a few pieces from the from Speckle server. So Ellen, and we have some people from White I drag out, and they collaborate on the server. So just to show you that we can drag out all the content and break it down. So these are users, Speckle collaborators. So this is a specific type. And just to show an example of when something is not mapped perfectly, these people work at the same company, but we have two different nodes. So that's where we have a clash in the interoperability. We need to be sure that we use the one White architects, not two different. So that's one part of it. Now, what we want to do is we want to connect to the DTCC platform, which is, in this case, it's a digital twin. So we do an extract from the digital twin to put out a part of the data. And this is some example data just to show the concept. So what we want to do is that we take some data out from digital twin, and then we continue with the design process. And the design process is taking place in Speckle so that the architects can work and do some calculation and generative design. And then, so we see here, we put it in here. And now on the canvas, we drag out the different models from Speckle. So here is one model, and the model have different versions. So now we can drag out two versions of the same model from the design process. So what we want to do with these versions is to put it in again in a digital twin at some stage, which means when we have done something. And now what we want to do is that we want to validate the data, because when you're moving data around in an ecosystem, you might break something like some properties or let's just pause here. Yeah, okay. It worked. Okay. Let's try. Oh, perfect. How am I on time? Perfect. Yeah, I felt stressed, but it's good to have a video, so I have to just rush it. Now I can take a breath, because that was a lot of information, right? So what we're seeing here now is that we use this tool to connect all the stuff, to break out who are the people, what are the versions, and everything. And the problem is that when we are moving data along between systems, we tend to break stuff because it's not interoperable with each other. It means that even if I write something, I'm not sure if it's really what I'm saying it is, because it's just a word. So we need this layer of what I'm talking about with ontologies and this kind of semantic layer, so that we can be sure that when I'm saying a building, I mean a building. So we are talking about the same thing, and that can be different. So the point here is that when we're doing the projects with interoperability, there are experts sitting for 5-10 years and building this kind of thing, which is very, very complicated and people don't understand it. So instead, what is good is to build a process so that we can start from scratch if we want in a project and build up the understanding of interoperability. But we don't want to start from scratch every time because we can reuse stuff. So you should basically work from where you are in the group, what kind of background you have and what kind of expertise you have, and try to build as fast as possible towards full interoperability. And this is a tool to help to understand where something is wrong. Here's something we need to fix. You can go in here and you can check and you can maybe add a few properties if it's missing. It depends on what kind of calculation you need to do. But when you're moving the stuff back into the digital twin, it should definitely be valid, because in the digital twin, there are some other rules or something that is, maybe this is a municipality system or something. They need the data to be valid. Yeah. Yes. So I think it's interesting from Parametric side. We are building the base bucket. It's an online canvas workspace to coordinate and break down complexity and sustainability. And we are looking for pilots. Thank you so much for that.
Here. Yes, my name is Alan and this is Jakob, and we are both architects at Liljevalchs Architecture here in Gothenburg. Liljevalchs has also offices in Stockholm and Malmö, and we have projects all over Sweden. Both I and Jakob are a part of the group called D+, which developing digital tools that we are implemented in all our projects in Liljevalchs. And these digital tools we are collecting in what we call a digital toolbox. And today we're gonna present two of these tools that we have developed within external projects, but also with knowledge and in collaboration with DTCC. And I will start present the glasshouse designer, which designed a new glasshouse with reused windows. And the main question we had for this project was, how can we effectively reuse residential windows into a new glasshouse while maximizing the amount of glass in the facade and ensuring a seamless construction process? And this is an ongoing project, but our work process so far looks like this, that we have made an inventory and we have collected a lot of data, which we have reported. And from that, we have created digital twins, which we have used with iterative design to create the glasshouse design. And when we made the inventory, we used the CC Build app. And for this specific task, it was important for us to get an ID for the windows, the condition status, and of course, the geometry of the window. We also attached a QR code to each window, and I will explain later why. It was really easy for us then later to just import this data into Excel, and then also to Rhino and Grasshopper, where we created our digital window twins. When we had these digital windows, and also the geometry of the wished glass house, we created a puzzler in Grasshopper with Python in Grasshopper, which placed all the windows into the facade, ensuring that one window is not used twice, and also that we had as much glass surface on the facade as possible. And here are just some design options that we got from that code. And of course, we got a lot of data with this as well. And the most important data was that the amount of windows used in the facade, and also which window we had used, the area of glass, and the area of field surface, which should be as less as possible. This data we exported back to the CC Build app, So when the builders on site, when they could scan this QR code, which we had placed on the windows, they got this new and updated information about this window. Of course, the window ID, but also the next status of the window. Not every window in this residential building should go to the glass house, but also to another project. And also they got information if the window should be on a renovation in the windows as well. For this example, you can see that window 101 should go to the glass house, and you can also see that it should be repainted, and you also see where the exact position for the window. As I said, this is an ongoing project right now, but we have some reflection for this work method. We think this process is quite good when using reused materials, and we think that the combination between an iterative design process and the computational design give us multiple design options, which we know all fulfill the design criteria, which is really good. And we see a big opportunity that the digital twin actually can communicate with the contractor and the whole project group in a much simpler and a quite fast way, which we see is really beneficial. We will see what this project lands, but we will have a lot of knowledge from this work method that we'll get into other projects when we're using reused materials and digital twins. So now I leave the word over to you, Jakob.
Yep, and I will talk about another practical application of digital twin cities, which we developed in our office in collaboration with DDCC, and that's our stormwater assistant, because we feel the climate is changing, and especially in Gothenburg, where we are located, it's more and more need for the stormwater analysis in the planning and design. We also feel there's quite clear statement of the requirements. We cannot worsen the conditions for existing buildings where we place something new. And we also are required to take care of a certain amount of water on the site of our property, which we're designing on. And the standard process as it is today in the detailed planning, it has its limitations. There is a standardized report. It takes a lot of time. You have to give it to external consultant. It's quite time demanding to process changes in it. And the visualization that you get is mostly two-dimensional, which is a bit harder to understand. So we felt the need to get a tool which is agile and will give us a quick response in our sketching stage mainly. And the digital twins here are really key to the answer, because you need quite a large chunk of a model with quite a level of detailing for the water to be flowing correctly. And also the open data are key to the answer, because we could download the underlag, the underlay for the large model from cities or open data. And we also could download the curve of the rain from the city's own rain simulation. And in that way, we can have the same conditions that the city is using. Our tool is a tool that is a terrain runoff. It's used mainly for sketching and early stages. It's done using Python and a Grasshopper inside Rhino. And it's referring to Swedish standards. It doesn't have right now any pipes or any porosity on ground. And we also did not implement any rapid river dynamics. But we are working on the pipes and on the porosity. And it's not meant as a replacement of the traditional stormwater report in the detailed plan, but it's more like sketching stage, quick iterations, being able to develop back, where do I need? Now I'm going to show a recent project, which is a school. And then we really wanted to see what happens in the moment when the stormwater downfall comes. Now it has come, and we could see that there actually is some dam which is causing some overflooding in the site. We could see one of the existing buildings is blocking the major flow to the site. Then we could also look where the water is piling up on the site. We could also look what happens more in the detail on the site. And there was a specific area which is called parking lot, where we had to have some discussions in the project. And therefore we did a detail study in that area. We tried to overlay both the water flows with the water depths to see where we have water both flowing and standing, and we could output the millimeters of the water level. And in the proposed situation, we got the building was given, but the landscape, that was our task. And here we really try to implement this new stormwater ditch to actually enable this major flow on the site. We also have been working with providing a safe passage for rescue, because when there's too much water, the rescue cars, they cannot pass through the water. And therefore we could secure even that condition. And we also wanted to see in detail, do the entrances ever get flooded, or have we designed it securely? We could also see what are the areas that get flooded first on the site, what gets flooded later. And here in this case, the entire courtyard in the north part of the building has been lowered to accommodate this huge amount of water volume. And of course, the biggest benefit maybe is the comparison existing versus proposed, and then seeing have we actually worsened the condition for any of the neighboring buildings. If yes, then we have to run some iterations. And here in this case, we could overlay, we could see, yeah, there has been one worsening. Then we would run the iterations and have it way more quickly than in the standard process. And we would also be able to output the total amount of water inside in time. And we also checked for control with the Gothenburg city's own calculations on the existing site. So to sum up, I think we managed to empower our own in-house architects with a deeper stormwater understanding. And we try to implement it as a natural part of our landscape design process or the city planning process. Because it really, we feel like it gives a more pedagogical views on the problematics, especially when it comes in 3D to people who are not stormwater experts. We lowered the competence threshold because it's our own people that can do it. And the feedback is way faster than in the traditional process, which clearly brings customer benefits. Thank you.
Very interesting to hear. Let me talk these things with you. Yeah, I'm from FOIAP. I'm Petra Jenning. I'm innovation lead at FOIAP. And I'm here today to talk about two projects that we've done that are affiliated with Digital Twin Cities. First one out is something we call Quadrat, and it's a tool for climate calculations in early design stages. It's financed by ETB2 and has the sort of the proper name there if you want to look for it. We're a bunch of organizations working together on this one. We asked ourselves how we can start to understand the building's climate impact from the very first sketches. And this question we asked ourselves quite a few years back now. And at that point, there were no tools at all out on the market for this. And we saw that there were lots of tools and ways and methods for climate calculations in later stages, but nothing in the early stages. The difference here is, well, there are quite a few differences in how you calculate and what's important in the different stages. But generally, we'd say that in the early stages, that's where we can have the biggest impact. We make a lot of decisions that does influence the climate impact of the building. So if we don't make the right decisions early stages, then it's going to be hard to compensate later on. We have a focus on geometry together with material in the early stages. Well, later stages, geometry is mostly set and it's just sort of material focus. In the early stages, we can sort of find the relationship and understand how material and geometry interact and behave together. We work with fairly rough numbers as there are a lot of unknowns. We work with generic climate data, and we developed a database of composite building elements and with their sort of associated emissions. But mainly, or most importantly, in the early stages, we really want the calculations to be sort of continuous, so we can do them over and over again. We want them to be interactive and in real time. So what we've done is that we connected up our 3D modeling design sketching tool environment, Rhino Grasshopper, with big sectors miljöberäkningsverktyg, which is developed by IVL, Swedish Environmental Institute. Not sure what the name is in English. And then connected to that, so that's sort of the base for the climate calculations. And then connected to that then is this material database that's hosted by IVL. And we have a tool for dimensioning that's developed by Tyrians, that's also acting in close to real time. Dimensioning is obviously super important when calculating climate impact. The quantity of materials matters. So if we sort of dimension wrongly, then that has a big impact. We also have a little tool for simplified heat loss number, and that's to make sure that we don't sort of do sort of the wrong decisions early on that then now my English is slipping here, that then is making it worse during the later stages when the building is actually being used. So therefore we have the heat loss to just make sure we have a control of the energy consumption. And we're working on integrating cost calculations in this as well. And this is sort of our, I don't know, ambition, what we set up. We should be able to just stretch and play and work with the building and sort of interact with the building. And then the whole time have an understanding of what the climate cost of this design is. If we go a little bit more under the hood, we have the rhino grasshopper environment at the bottom, and we have BM environment at the top here. And so what we do at our end is that we do volumetric sketches, and we bring out the quantities, and then connected to that is we bring in this building element database with the associated emissions, and then we attach them to each other, we send it back to BM, they do the calculation, and they send back the results to us. And this is more or less real time. We're under a second. And then we have lots of examples of where we use this. I just brought one with me today. This is a building that we're working on in Stockholm at the moment. And here we have compared 3 different construction methods, steel, concrete, and wood, and playing with this building to see how we can make sure it's the best from a climate perspective. Yeah, that's our work on the climate tool, and the plan is and has been all the time that we're going to release this connector between Rhino Grasshopper and BM as open source, and we are still working on that. So it will come. Promise, it will come. I've said that so many times now. But the next project I want to touch upon is something we call robotic brick. It's a part of a sort of longer commitment in robotics that we have at FOIAP. We've been part of starting up the construction robotics lab at Lunds University. And here is a little project that we've done as part of that with this group, and this has been supported by Smart Build Department. And here I have a film. So I'm just going to start that. But we have no sound, so I'm going to talk. So we are on site, and we are constructing a little fire pit next to a future cafe. And we're looking at then, bricklaying with a robot, and we also implemented that we have the mortar included here. And this is my colleague Henrik Malm that's been in charge of this project, and he's also the lead for the architecture and structure part here. Still up. This was an event we had in June, where we made this sort of little structure over a day with the robot working, and that was it.
Yeah, exactly. I worked with my chapter together on this milestone project at Chalmers, and the project is called Twin Refab, and we're investigating in how we can enable the reuse of building components that are from deconstruction sites or from renovation sites, and that would be too broken to be reused currently. So we're looking into how we can actually digitize these elements and then kind of analyze them and do something with these elements so we can reuse them in a new project. And especially elements that currently would end up on the landfill probably or be recycled and not be reused. And we try to integrate for that a lot of different new technologies like digital twins, of course, computer vision, parametric design, then robotic 3D printing, and also a little bit of machine learning. And our research is kind of structured in these 3 parts. So first we investigate how we can actually create a digital twin from an element. So we just have a raw element that would be thrown away. So we take it, and how can we create a digital model of this? And how can we also automate this process so we don't have to manually 3D scan, but how can we maybe use a robot to do the 3D scanning for us? What data are we actually able to get? Is it just a point cloud? Can we generate a mesh from that? Can we separate the mesh into different parts? And then also, how should we store this data so it can later be reused? And maybe if there's new ways of interpreting the data, that we still have the raw data in a format that is accessible. Then also then analyzing these components, like what is actually broken about it, what needs to change so we can create something new from it. For that, we are trying to use some machine learning for like a semantic segmentation. So we have this one point cloud for this one mesh, but we try to separate it into all the objects that make up this bigger object or element. And then also see if we automatically can generate kind of like like a new intervention to repair this object and make something new out of it, or to actually make it into the same object again, but repair basically. And for that, we're also looking a little bit into like generative AIs. And then the last step is kind of printing. So we're using 3D printing. So how can we generate toolpaths onto these objects? How can we optimize these toolpaths, collision avoidance? How can we print on objects? Like how does the printer need to work for that? For example, like maybe if you're trying to print onto an element, on the sides of it, you need to kind of angle the print head and things like that. And then also, how do the filament and the elements actually interact with each other? Like most people just print on, like, of course, a planar surface, but if you have like a more shaped surface and you print on it, what actually happens to the filament on interaction of these 2 elements? So for that, we have this robot, and we put the Kinect, this device on it, which can do 3D scanning and also picture scanning, like color picture scanning, and then also a 3D printer extruder on it. And we have it on the same device because we really want to investigate if we can have this integrated workflow of putting a piece onto the table, the robot scans it, generates a path, and then prints this path. So from the scanning, we get these sort of point clouds. And these we can then interpret into like a mesh. And because we have color data as well, we can also kind of interpret it as like, of course, like a colored mesh. And then we can analyze these objects with different algorithms. For now, we kind of look into more like wooden objects and see what we can do there. And for example, in the wood, we can do things right now, like detecting where the grain works. That's what's just like a trial on how computer vision algorithms kind of work in this area. But then also with machine learning, we can do a complete semantic segmentation of objects. So see all the different parts of the object, like the knot here or the bark and so on, like can find the different areas of an object. And then based on these found features, we can generate paths, for example, here based on the geometry, or here based on this found knot that like ignores that. And then this one is like the first sample. Maybe you can give it around. And while we, for now, just investigated on like these smaller wooden blocks because it's very accessible and it's like a quick iteration cycle, in the long run, we of course want to take real objects. So we have some trial objects that we want to investigate further on. For example, a broken window, there's like some paint that's splattered off, there's some wood that is broken off, the glass is a bit broken, and then see what different interventions we can find to repair this window to make it a new object or to make it a new sort of window in some place. Or for example, also looking in a lot of old wooden flooring, which is in renovation sites, of course, something that's often thrown away. How can we enable the reuse of that? but then maybe also to investigate how good our representation of scanned data is. We are looking into, for example, recreating old roof tiles, so that we, if there's roof tiles missing, we could like kind of reprint the same tile. Yeah, these are kind of the different interventions that I just mentioned.